recording, so whenever you're ready, you just take off.
All right. So today, welcome class. Welcome back to my classroom and Hindo's classroom. And today we're going to talk about Snell's Law and refraction in general. So, first off, when light passes through a transparent medium, it will bend. So what happens is that the light coming in will slow down, and as it slows down, it tends to bend. So we see this with lenses of any type. You have examples. Your eyes have lenses in them that will bend light. Prisms will bend light, and so we have many different things that will do this. If you look at water and you can see the object should be right there, but it's not. This is due to refraction of light going from air to water. So first off, let's look at a prism. So as light comes in, as it goes from one medium, air, to the prism, whatever plastic or glass it's made of, it will slow the light down. Light will change its speeds based on the medium that it's in. And different wavelengths of light represent different colors, different parts of the magnetic spectrum, electromagnetic spectrum, and therefore they will bend at different rates, those different wavelengths. And so that's why a prism can separate out light, because it will refract the different wavelengths of light at different angles. Okay, now let's look at an example up here of light being bent. Okay, so what we have here is three laser beams coming out. They are going straight and going through air, but as it passes through this piece of plastic here, it will bend. And this is actually a converging lens as the light tends to converge together. We also could put a diverging lens there, and as you see, the light is diverging from it. All right. So what is Snell's Law and how does it pertain to refraction? Well, Snell's Law, the equation is N1 sine theta 1 equals N2 sine theta 2. That is Snell's Law. All right, Mr. Nishad's going at a snail's pace here. Get your point, right? Well, I will try. So first off, we have to understand what N is. N is an index of refraction. Make note that Mr. Bishop and I have put on the capa assignment, the N, a list of common N values for substances that you will need for your capa problems. It is in the very folder of your online mastery problems. It is also in the packet sent home to you if you're not able to get online, so it is in both places. So we need to understand what these pieces are. Well, for Snell's Law, N stands for the index of refraction, and it stands for the velocity of light in a vacuum over the velocity of light in that medium. Okay, so what we have here is we know the velocity of light in a vacuum is 3.000 times 10 V8 meters per second. We at least know that. So we can then calculate if we're given different velocities, if we're given the velocity of the light in the medium that it is going into, we can calculate N value. But for many problems, we just look at the table of N values that we have been given. All right, so now on to theta. So this is substance 1. You can call this substance 1, or A. And over here would be substance B. So one side, the other side. Doesn't matter which one you call A and B, but it's one side for one and one side for the other. Now, if we get onto this example right here, we have substance A, and light is this beam coming in here. Okay, so our surface is right here. The angle, theta 1 and theta 2, are always with respect to the normal. If you recall, normal in physics means perpendicular. So perpendicular to the surface, you draw perpendicular, and between the light ray and the angle, or the light ray and the normal, that is the angle in Snell's Law. Not with relationship to the surface, it is the angle that is in relationship with the normal. So there's theta 1. So substance A, that index of refraction there. Theta is this one. Substance B This is substance B side. There's your normal. There's your light ray at bent. That's theta 2. And we use the n value for substance B. Let's flip the third surface on the side here. Same thing though. Substance A, your light's coming in with respect to the normal, not with the surface. It exits like this, and therefore the angle is with respect to the normal still. This is substance B. So you still have your formula. You can call this NB, theta B, and NA, and theta B if you would rather use those subscripts. So that is how those are the parts of the formula. It's also interesting to note that if you go from a higher index of refraction substance to a lower, it will bend away from the normal, okay, because it is speeding up. And if you're going from a substance of higher or lower to a higher, it does the opposite and bends toward the normal. So that is what dictates whether you're going toward or away from the normal. The index of refraction going from a higher to a lower or lower to a higher. Okay, so problem 1, finally to it. So right here we have a beam enters water at an angle of 35.9 with respect to the vertical. That should be that is given to you in the problem. So we know that's the one that's going to be going into Snell's Law here. So first off, we can draw a picture, which will be helpful. So we have our water, okay, and we have a light ray that is entering water, okay, so we have it here, and that 35 degrees is with respect to the vertical. That is very important to note, because if they gave you with respect to the horizontal here, the surface of the water, you'd have to do 90 minus that to get this, because that's the angle that goes in Snell's Law, always with respect to the horizontal, and it always spits out with respect to the vertical. Sorry, the vertical. So it's always with respect to the vertical that goes into Snell's Law, the normal. Now, we are going from air. Air has an index of refraction of 1.000293, and water is 1.333. Okay? So now, we're going from a lower to a higher. It's going to bend toward the normal. So here we go. It's going to bend this way. Okay? Now, we can make it a little bit better so we can see it easier there. Okay? And so then this is theta 2, or theta water if you wish. Make it theta W. So now what's our formula? N1 sine theta 1 plus N2 sine theta 2. Oops, equals. So it's N1 sine theta 1 equals N2 sine theta 2. And now we know the N of air, so this will be our air side. This will be our water side. And we will have and N2 is 1.333 sine theta 2. Now, just make sure your calculator's in degrees and solve, and you'll get this to one side, and then you end up with sine theta. And how do you undo sine? You do the inverse sine as your final step, and that should give you the answer.